Hello everyone, Mr. LaRusso here with another online lesson. Specifically, we are moving on to the next unit called Dynamics, which specifically is the study of forces. So let's talk about the difference between dynamics and kinematics first of all. Kinematics is the study of how objects move, where dynamics explains the reason why. So dynamics is basically a study of forces. So what is a force? Well, a force is a manifestation of energy that moves, reshapes, or tends to move, reshape an object. Or in plain language, a push, pull, squeeze, or stretch. Forces are vectors, which means that they have both a magnitude and a direction. Forces, not surprisingly, are measured in a unit called newtons, which quite obviously is named after English physicist Sir Isaac Newton. A newton is defined as 1 kilogram meter per second squared, and this unit will at this moment make 0 sense to you. It won't be apparent what that means until we take a look at Newton's second law, which will be in the next lesson. Forces, the way they are measured traditionally, are with a calibrated spring scale, similar to what you would find in a grocery store or on a scale that you have at home, based on the compression, squeezing, or extension, stretching of a spring. Now, before we get any further, we need to clarify a couple of ideas. In plain language, the concept of weight and mass are often used interchangeably, but in physics, they very specifically have a different definition. So here is the main difference. Mass is defined as the amount of material in an object, and it is measured by using a balanced scale, kind of like the triple beam balances that you use back in grade 9. And the standard unit is the kilogram. So it's really just a measure of how much stuff is in an object. Weight, however, means something slightly different. Weight actually represents the force of gravity acting on a mass. So this is where the big idea comes from, where in space you can be weightless, but you are not massless. So if you are in orbit, for example, you will experience what's called 0 G, so you're floating around, but your mass remains the same. And that's the key difference. So whenever we talk about weight in physics, we refer to weight as the force of gravity. So weight equals force of gravity, which means that whenever I ask you to answer how much something weighs, you don't measure it in kilograms, but you measure it in newtons. So to calculate weight, we have a formula, and the formula is as follows. Force of gravity is equal to the mass times the acceleration due to gravity, represented by little g. So I want to actually get into a little bit of detail here, just so we understand the notation. F obviously stands for force. The subscript g represents the type of force that we're referring to, which is gravity. M is the mass of the object, and little g represents what is called the magnitude of the acceleration due to gravity. So let's talk about that in particular detail. In kinematics, we refer to acceleration due to gravity as negative 9.8 meters per second squared. The negative implies that it's going down. Whenever we use the symbol little g, that actually just refers to the magnitude of gravity, which is just 9.8 meters per second squared. Because this here is just a measurement for the magnitude of the force of gravity. We'll talk about how to deal with the directions a little bit later. Let's take a look at an example here. So we want to find the weight of a 20 kilogram mass, and it's very simple. We can just use the formula, M times G. All right, so the mass is 20 kilograms, and little g is defined as 9.8 newtons per kilogram, and then the kilograms cancel out, we're left with newtons. The other way to measure it is 20 kilograms times 9.8 meters per second squared, and then we get that kilogram meters per second squared. And as you recall a little earlier up, we said that 1 newton is defined as 1 kilogram meter per second squared. So generally speaking, however, I don't expect you to go with this much detail when solving these. This is just more so to explain the concepts. But this, I don't usually have students put the units in. So normally, if you were to be asked to find this, you would simply write the formula first, Fg equals mg, and substitute in your values without units. Notice g is 9.8, not negative, and that is equal to 196 newtons. Simple as that. The next concept we have to deal with is something called a free body diagram. Whenever we're solving problems in physics, specifically with dynamics, I should say, is that we need to actually have an analysis of what is happening with the objects in terms of the forces acting on them. So here are some of the rules for these free body diagrams. You draw a diagram of the object, and this is key, isolated from its surroundings. You draw a point in the approximate location of the object's center of mass. From that point, draw all the forces acting on the object and all the forces acting specifically on the object. Do not include the forces that the object exerts on other objects. And then we label it FBD. Let's consider this example here. We have a 10 kilogram mass and it's hanging from a string. So this would be our ceiling, this is our string, and here is our mass. The free body diagram looks as follows. The box represents our 10 kilogram mass. This can be either a rectangle or it can be a circle. Generally speaking, most of the times will use a rectangle unless the object happens to be spherical, and I will actually use a sphere in that case, but generally speaking, it's a rectangle. Now, I want you to notice something about the vectors, the force vectors in particular. Notice that the magnitude of the two vectors, and remember, magnitude means the size of them or the length, are equal to each other, but they're in the opposite direction. What that implies is that the net force acting on this mass is zero. F net would be zero, because the object is not accelerating. We haven't talked about what that means yet, and I haven't brought up the concept of F net, but F net refers to the sum of all these forces. So let's think of it another way. Think of this as a tug of war. Fs is on team up, Fg is on team down. When the mass is stable like this, that must mean that the downward force must be counterbalanced by the upward force, so they cancel each other out and the object does not move. And this is how you draw a free body diagram. Next concept is something called the normal force. The normal force is a force that opposes gravity, and it's specifically created by surfaces themselves. The question is, what do we mean by normal? In math, normal actually means 90 degrees. So when you see the word normal, and you may remember this from optics, when two lines are perpendicular to each other, we call this a normal. We call this a normal. So this vertical line is perpendicular to this, so 90 degrees means normal. So let's talk about what this looks like in terms of the free body diagram. When we look at this free body diagram, the normal force, and notice that it's a capital N, is equal but opposite to the force of gravity. The curious thing about the normal force is it automatically adapts to the amount of weight placed on it. So for example, if I was to place an additional 20 kilogram mass, the table would compensate for the additional 20 kilograms. But that's obviously only up until a point. So what is generating this normal force? It actually has to do with the fact that this wooden table flexes slightly. And when it flexes slightly, it's actually the force of the atoms held together by the electrostatic force that opposes it. If you recall at the beginning of the school year, I talked about how atoms are generally further apart and atoms naturally repel each other. But when you start compressing an object, you're forcing the atoms to get closer to each other. When the atoms get closer to each other, they increase their force of repulsion. So when you place a heavy object on a surface, that object compresses the surface slightly until the counterbalance force of the atoms themselves go equal and opposite. That's how things get dented. If you leave a heavy object on the soft ground, eventually the ground gets compressed a little bit where that object was. And that is how the normal force can seemingly always compensate for how much weight there's on. It has to do with the material itself compressing slightly, even if it's not obvious to the naked eye. Next concept is something called the net force. I alluded to this a little bit earlier, and we can take a look at this object right here. When you look at a 20 kilogram object sitting on top of a table, if the table holds and doesn't break, we know that the object just stands still. It's not going anywhere. And the reason why that is that the weight of the block has to be counterbalanced by the normal force. and they're equal and opposite to each other. And as a result, the object doesn't accelerate. Specifically, it doesn't move. But the net force isn't just two forces necessarily. It's the sum of all the forces acting on an object. So let's take a look. The net force is defined as the sum of every single vector acting all the way up to the nth vector. You can have multiple forces, and the net force is the sum of all of these individual forces. Another example. Let's say you're trying to push a box across a table, but the box is very heavy and you're not pushing it hard enough in order to get it to move. What would the free body diagram look like in this case? Well, without us intervening, the object itself has its weight, which is the force of gravity. The object is counterbalanced by the normal force. Then we have the applied force. Now, as I've drawn the diagram, it looks like the object should be moving forward, but there's another force that I have not talked about yet, and that is this opposing force, which we know as the force of friction. So that's what this free body diagram would look like, of a heavy object on a table being pushed but without sufficient force to actually cause it to move. What you can see is that there are four forces: the normal, the weight, the applied force, and the force of friction. And you can see that there's both a vertical and a horizontal component to this question. So all the forces in the vertical cancel each other out. All the forces in the horizontal also cancel each other out. And as a result, we have a net force of 0. So when the net force is equal to 0, the acceleration of the object is equal to 0. Now notice I said the acceleration. I didn't say that the object is necessarily stopped. I said that the acceleration is equal to 0. And we're going to specify other circumstances where we can have a net force of 0, but still be moving. The other term for this is a state of equilibrium. So when F net is equal to 0, we can say that the system is in a state of equilibrium. And that's when the forces are balanced. So when the forces are balanced, our net force is equal to 0, and the object is either at rest or moving with constant velocity. This is the one that most people have problems with, the concept of something moving at a constant velocity. A good way to think of it is what happens when you're driving your car. When you're driving your car, and let's say you're getting up to highway speeds, you are required to keep your foot on the gas pedal in order to keep the car moving forward. The reason being is that the engine has to push just hard enough to fight the wind resistance and the road resistance. If you take your foot off the gas pedal, the car is going to slow down and eventually come to a stop. So in the situation where you're going at a constant speed, not speeding up or slowing down, but staying at a constant speed, that implies that you are moving at a constant velocity. In order for that velocity to be constant, that means the forward applied force from the engine must be perfectly balanced with the force of friction and air resistance pushing the car back. So a car traveling at a constant speed in a straight line, that's also considered to be F net equal to 0. So acceleration only occurs when the forces are out of balance. So if F net is greater than 0, then the object is going to accelerate in the positive direction. When F net is less than 0, it's going to accelerate in the negative direction. So very specifically, acceleration is calculated only using the net force, not the individual forces themselves, but the overall force. So let's take a look at these diagrams and look at how the objects would ultimately move. So when we have this particular diagram here, if we notice, F1 is larger than F2. So F1 is going to win the tug of war. So the net force is going to be the sum of these two vectors. Well, F1 is positive, F2 is going to be negative. And when we add them together, you can see that the net force is smaller than F1, but still in the positive direction. This is also the direction that the object would accelerate. Now let's take a look at the second example. Here's F1, here's F2. They are perpendicular to each other. F1 is going to cause the object to move towards the right, or in the forward direction if you wish, or east. F2 is going to move up, or if you prefer, in the north direction, depending on your perspective. So the two combined would end up having a net force on an angle like this. Since F1 has a larger magnitude at F2, our theta here is going to be less than 45 degrees. And then when we take a look at this final diagram, we have a tug of war in the x-axis and no tug of war happening on the y-axis. So between F1 and F3, F3 is going to win this fight. So we know that the object is going to accelerate towards the west. But F2 is unopposed in the y-axis, so not only is this object going to accelerate in the west, but it's also going to have a northern component as well. And that's why FNet looks the way that it does.